Welcome to the second part of lecture 20. So, in this lecture we learn one more characterization of planar graph using edge contraction, and we will also prove that every planar graph is 6 colorable. Of course, we know that every planar graph is 4 colorable, which is the 4 color theorem, but we are not going to prove that, but we will be proving that every graph is 6 colorable. So, I will start with another characterization of planar graph using edge contraction. So, this is a theorem due to Wagner 1937. A finite graph that means it has finite number of vertices is planar if and only if it contains no subgraph that is edge contractible to K5 or K33. Okay. So, again I am not going to prove this theorem, I will just give an example to say that how do you show to show that how to prove graph is non-planar using this theorem. So, the Petersen graph is non-planar. So, here is the Petersen graph. Right. So, the edges are like this. Okay. So, this is what the Petersen graph is, and we know what is the meaning of edge contraction, right. Contracting this edge, please recall that this is what the edge contraction is. Suppose this is the edge u v, if I want to contract the edge u v, so I will get this graph after contraction of the edge u v. So, this edge u v will be removed, will be deleted, and then these two vertices will be merged into one vertex. Okay, now we can prove that this is this graph is edge contractible to K5. K5 is complete graph with 5 vertices. Now, you can see that you can get this K5 from in fact, the Peterson graph is edge contractible to K5, because if you say if you contract this edge, you contract this edge, apply edge contraction on this edge, this edge, this edge, this edge and this edge, you will get this graph K5, right. So, when you apply edge contraction on this edge will be deleted and these two vertices will be merged and you will get something like this, right. And after edge contraction, these two vertices will be merged into one vertex. This is what you will get. Similarly, these two vertices will be merged into one vertex here, and these two vertices will be merged into one vertex. These two vertices will be merged into one vertex. So, it is easy to see that Peterson graph is edge contractible to K5. So, Peterson graph is non-planar. Now, we will talk about coloring of planar graph, and we will prove that every planar graph is 6 colorable. So, for that we need some more result. Here is one of them, lemma 4 maybe. This says that every planar graph has a vertex of degree less than 5. Okay. Suppose every vertex in G has degree greater than or equal to 6. So, what we are going to prove that every planar graph has a vertex of degree at most 5. So, we first assume that every vertex in graph G has degree greater than or equal to 6, and then we will come to a contradiction. Then the degree sum, which is equal to 2e, 2e is the degree sum, we know that, and what we are doing is that I am replacing, so each degree is greater than or equal to 6, so it can be more than 6, I am replacing them by a smaller quantity, so 6 only, and there are v many vertices, so it is 6v, which implies v is, which implies E is greater than or equal to 3v. But we know that if G is a planar graph, then from the first lemma, that then the number of edges is less than or equal to 3v minus 6, and this contradiction, but what we got here is that E is greater than 3v. So, this contradiction shows that at least one vertex has degree less than equal to 5. That means, every vertex in the graph G cannot have degree greater than or equal to. Next, we prove the concept of K degenerate graph. Okay, so a graph slightly complicated. A graph is K degenerate if each of its subgraphs has a vertex of degree at most k. Okay, so a graph is K degenerate if each of its subgraph has a vertex of degree at most k. We will try to understand this one. Let me write down the characterization of K degenerate graph and then I will explain. So, a graph is K degenerate if and only if there is an ordering of the vertices V1 less than V2. This is not less than, it is a ordering Vn, ordering of the vertices such that each vertex Vi has at most k neighbors to its left. Then we say that the graph is K degenerate. Okay. Let me just give an example of a two degenerate graph. So, this graph okay. So, this is the linear ordering of the vertices, and then now I draw some of the edges. Well, these two are adjacent and there is nothing specific with this graph of course, but what I am trying to make sure that every vertex in this linear ordering has at most two neighbors on its left. Now, you see that this vertex has one neighbor to its left, this vertex has two neighbor, this one and this one on its left. Similarly, this vertex is also having two neighbors on its left. This vertex has no neighbor, at most two neighbors. So, this vertex has 2, this vertex has 1, this vertex has 1. So, this is a two degenerate graph. because of the fact that now you take any subgraph of this graph, then you can always see, suppose I remove this edge, I take this subgraph of this graph. Now, it is always true that the rightmost edge, sorry, the rightmost vertex has degree at most 2. So, that ensured that the graph is too degenerate, because each of its subgraph has a vertex of degree at most 2. So, this linear ordering, what it does is that it makes sure that whatever subgraph you take of this graph, the rightmost node has at most 2 degree, right. The way I showed before, that if you remove, so this is a subgraph of this graph G, and you can see that the rightmost node has degree at most 2. So, and this is true for any subgraph, it is not that particularly for this subgraph. If you take for example, any other subgraph, of course. Yeah. So, this is an example of a 2 degenerate graph. Let me just give another example of 1 degenerate graph. This graph is 1 degenerate. Why that is true? Because if I take this ordering, I put this vertex, say A, B, C, D, E, F, I put the vertex A at the beginning, and then B, C, D, E and F. So, what I get is that I get this C is adjacent to A, everyone is adjacent to A, and F is also adjacent to A. So, you can see that in this linear ordering, every vertex in this linear ordering has at most one edge to its left, at most one neighbor to its left. So, that is why this graph is 1 degenerate graph. I hope that now the definition is clear and the characterization is also clear, why it will be while a graph is k degenerate if and only if there is a ordering of the vertices such that each vertex V I has at most k neighbors to its left. Now, the degeneracy of a graph of the graph G, which is denoted by delta star G, is the smallest k such that k is such that G is k degenerate. Right. So, this is the degeneracy of the graph G. Now, if you remember the greedy algorithm for graph coloring, if the graph is k degenerate, that means in this linear ordering it has at most, for vertex I there are at most k vertices, k neighbors to its left. So, when the graph has degeneracy delta prime G, that means the graph has for if you have a linear ordering of the vertices, and then every vertex V I has at most delta star G neighbors to its left. So, that is why using the greedy technique you need the number of colors required to color the graph, which has degeneracy delta star G is delta star G plus 1. As I told just now that suppose this is the linear ordering of the vertices of a graph which has degeneracy delta star G. The meaning of this one is that the vertex V I has the vertex V I in this linear ordering has delta star G at most delta star G neighbors to its left. So, using the greedy technique you need at most delta star G plus 1 color to color the graph G. Well, so we are sort of ready to prove the theorem that every planar graph is 6 colorable. Okay, so this is almost we have to combine many results, previous results together to prove this. First of all, let G be a planar graph. Then this is easy to observe that every subgraph of G is also planar, right, and hence has a vertex of degree at most 5. This is what we proved just now, that every planar graph has a vertex of degree at most 5. So, G is a planar graph. So, every subgraph of G is also planar, and so every subgraph of G has a vertex of degree at most 5. Hence, in terms of degeneracy of the graph, G is 5 degenerate, right. So, once we know that G is 5 degenerate, we can use this proposition that 5 degenerate means in the linear ordering of the graph G, every vertex V I has at most 5 neighbors to its left, right. So, you need at most 6 colors to color the vertices of this graph, right. Hence, that is using the greedy algorithm. Thus, chi of G is less than equal to 6. Okay. So, we have proved that every planar graph is 6 colorable, and since the graph, every planar graph is 5 degenerate, we have a linear ordering of the vertices, and we know that the ith vertex, just recall the greedy technique of coloring the vertices of a graph. Then as we know that Vi has at most 5 vertices to its left, you need at most 6 color to color the vertices of the graph. So that is why every planar graph is 6 colorable. Now there are results, more stronger results theorem, which is 1890 result. It is called 5 color theorem. And it has been proved that every planar graph is 5 colorable. Okay, again we are not going into the detail of the proof of this theorem, 5 color theorem, and the final result, the stronger result that we have till date is that 4 color theorem, which is 1976. It is called 4 color theorem. So, the 4 color theorem says that every planar graph is 4 colorable. Again this is a very long proof, so we are not going into the detail of proving 4 color theorem. So, what we have proved in this last lecture is that we have proved that every planar graph is 6 colorable, and then we have stated 5 color theorem and 4 color theorem. That is all about coloring planar graph, and this is the last lecture on graph theory. I hope that you will enjoy this course, and I would like to thank the NPTEL team in IIT Madras. More specifically, my special thank to Bharti and my cameraman Ravi for giving me all the support I require to record these courses. Thank you very much.